To the end of this course, COMSC 142. The semesters end quite quickly, so here you are. There's only 2 more lectures and no new material in the last class. I've updated the stores in Canvas, and several people already have an A. If you have enough points to have an A, you do not need to do any more projects for the final exam, although you're welcome to, but it won't affect your grade. And if you don't have enough points, you still have time to turn in more things and accumulate more points, perhaps take the final exam, another clear source of points. Just make sure you get everything in by 12/12. That's when the semester ends, and after that I have to turn in the grades right away. So anyway, you should be able to see your scores in there, and that would guide you. So let's take a look at the chapter 13 about the operating system. So if I get this thing to move, there we are. So we'll talk about booting and running, processes, virtual memory, and inter-process communication. So the operating system manages the hardware. That's the purpose. It manages hardware resources like the keyboard, the monitor, the RAM, the processor itself. And so your user programs go through the operating system in order to get to the hardware. Your user land programs do not have the ability to directly talk to hardware. Now, this also runs, therefore, multi-programming. More than one program can run at a time. The processor can only be doing one job at a time if it has only one core. Although most modern machines do have multi-cores and, in fact, can be doing several things at the same time. But anyway, what they have to do is organize this so every program can move forward and they don't interfere with each other. So the kernel is the heart of the operating system that must always be loaded into RAM. You can't run the machine without the kernel in memory. So it's relatively small, and it's the core of the operating system. And so that sets up abstractions, like deciding which process gets CPU time next. This is all done by system calls, and you've seen this from our assembly code. The way you get anything done is you fill some registers and do int80 to call the operating system. The operating system is the only thing that can touch the hardware, so to get anything done, you just set it up and ask the operating system, please do this for me. So your user program goes through the system call interface and sends a system call in, which goes into the kernel, which then goes through disk drivers to reach the hardware or directly to the CPU and the RAM. That's its purpose, is to manage access to all the hardware. So when you boot up the machine, you start a program. You start running your program, it loads the binary from the disk into RAM and runs in RAM. It makes a copy of the data on the disk into RAM, and then it creates a new process and tells the CPU to run a new process, which then allocates some RAM and other things for it. Now, when you first boot up the operating system, it finds non-volatile code in either BIOS or UEFI, which is just fixed code to get the machine started. And what this does is it looks for a storage device that hopefully contains an operating system and copies that operating system into RAM and initiates it. So its main purpose is to handle very simple access to the basic hardware, like a keyboard, a storage device of some kind, and a display of some kind. So that loads the OS in from disk and gets the system ready to use. So now modern operating systems are all interrupt-driven, which I was very interested to find out. They're just sitting there waiting. And then every time something happens, they get an interrupt saying, stop what you're doing and do this other thing. That's how everything happens. So there are 2 things called interrupts and traps that are very much the same thing. Hardware interrupts are ones that come from hardware, like somebody presses a key on the keyboard or the packet comes in your network card. That's a hardware interrupt. And the software layer is when an application makes a call, like the ones we've been writing, where you run a program and it calls int80. That makes a trap, a software interrupt. Both of them cause the operating system to say, wait, you have to start doing some work. Add this to your work queue. All right, and you can also have exceptions like disk read errors or divide by 0, which are interrupts caused by error conditions. So here, if you did a write system call, this is how you write to the screen. You just fill up some registers, you store some data somewhere, you put a pointer to the message here and a link there, and you do an int80, and that will make a system call, which will read these parameters to decide what to do, and then you have another int to exit the program. So the interrupt bus sends a signal from hardware to the CPU, and the CPU then runs an interrupt handler. User mode is where everything you launch starts. Everything after you log in, from the start button, from a terminal, anything you do is in user mode. This is a sort of sandboxing where your code runs in a limited environment. You do not have access to all the operating system commands. And the point is, this code is likely to be flawed and have problems. So if something goes wrong in user mode, the program can just stop and put up an error message and you can relaunch it. It doesn't stop the computer completely because the kernel mode is what would do that, and you don't have access to that directly. So all this can do is live in the little area allocated to it by the OS. It can only use the part of memory it was given to use. And this should say data, by the way. And it then can send things to the kernel, and the kernel will execute them. So the process has an address space, room for the text, which is the code, the data in the heap, and the stack where it runs. And originally, the kernel was mapped into the address space of every process. They've changed that to something different in 2018 because of the Meltdown hardware exploit. There were a whole series of hardware exploits based on speculative execution called Spectre and Meltdown and many others. The fundamental efficiency features of the processor lead to an insecurity, and we're still struggling with that in the industry. There are many, many exploits, many, many attempts to patch it. None of them have been perfect, and the exploits keep coming out. So, processes is a running instance of a program, so it's got executable code, data, and the context of the program, which is things like its register values, like the instruction pointer. And in a multi-programming system, there are multiple processes running at the same time. So each process feels like it's like it was in a virtual machine. Each process feels like it's alone, and it has its own memory and its own processor to use. And they can run without interfering with each other, which is part of the operating system's job. Now, it's actually going by time sharing. Each process gets a certain number of cycles, and then it has to let go and let somebody else have some cycles. So it really runs intermittently, moves forward a bit and then stops, like at a red light, moves forward and stops. But of course, this all happens very fast, so the user doesn't perceive this normally. And it does it with context switching. It is therefore, if you stop one process and start another process, there's a cost to that. You have to save the condition, the context of the current process, like its register values, and then you have to load the context of the other process. So context switches do cost some time, and if there's too many context switches, they slow down your machine. All right. So each process has a unique identifier, and there's a command that will show the PID values. It has its own address space. It has its execution state, like the register values. It has open files, and it has other resources, perhaps. And the state determines whether it's eligible for execution. So you may get a process ready, then you run it, then you're waiting for an event, like you might be ready for the user to type in something on the keyboard. So the process is now blocked. It can't move forward until this event happens. Then the event occurs and it can begin running again. So fork is how you create a process. And in early versions of Linux, every single process started from init. When you boot up the machine, the one process starts called init, and every other process is a fork from init. And I think it still works that way. So when you fork a process, there are now two identical processes, although they get allocated their own individual memory and such. So the parent process is the one calling the fork. The child is the new process it creates. And so now they both proceed from that point on. So they both have exactly the same instructions. And you have to plan for that when you write your code. So, for example, in this one here, you have a main program. Now it creates a new child process with fork. So both parent and child will execute this. And so what happens is you'll see PID is this and PID is that. The child has always got a PID of 0, and the other one has another process ID. So they're both going to do exactly the same thing and exit. That's the simplest fork demo. So the fork returns 0 to the child process and the parents and a real PID value like 14 to the parent. So you could put an if statement in. Create a new child process, and if it's 0, then print child, otherwise print parent. And so when you run this one, you'll see parent and child. So there you go. Now there's another thing you can run to actually get the real process ID, which I think is PPID. There's get PID. Yeah, my PID. Get PID is here. Yeah, PID is fork. So when it creates the new process, the process ID starts out at 0. If you examine it later with get PID, you'll get its actual process ID. So you can see that here. The original parent was 6645. The child is 6646, which makes sense. All right. So then they're each running independently. So if you the parent and child could run, the child could print out first. They could come out in different orders. They're both running forward, and other things may interfere with them, so those two processes may not run in synchrony. All right, so exec overlays the calling process's image with the new image on a binary file. So instead of making a fork that's identical to the parent, you create a new process with different content. So here we exec ls. So now when you run it, it's going to fork and run ls. And ls will list the current files. All right, so that's what happens. You do a fork, and then that creates a child, and the child then executes ls and replaces the running program with ls, so it never returns. Exec VP never returns. At this point, your current process terminates and the new process launches running ls. You never execute these statements down here. It never gets there. Exec VP leaves and doesn't come back. All right, that's the game. Okay, so let's try Kahoot, which are here. 13A, I would think. I must be wrong. Well, it must be 13A. All right. We have 6 people online. We may get some more Kahooters. There we go. Get one more. There'll actually be a bit of a contest here, but anyway. All right, I guess that's it. All right, so which item manages the file abstraction? The kernel operates it. It creates this thing called a file, which is a sort of virtual way to read and write data from the storage device. All right. All right, which one can be ready or running? That's the state of your process. It's ready to go or running. It could also be blocked. There are other possibilities. And what function overlays the running process with a different program? VP is the right answer. I'm going to make a note, 13A. I made a note to fix that later. All right, so let's carry on here. All right, so exit and wait. So you can complete all your code and return from the main function, or you can perform or invoke the exit call, or you can crash by performing an invalid action like dividing by 0, or you can receive some signal that tells it to execute, like what happened in Windows if you go to Task Manager and terminate it. So, all right. These send various signals like this, SIG, SEGV, and other signals, which are interrupts. There are traps, I suppose you'd call them, signals that are sent to the operating system to tell it to do something. So this is for null pointer dereference. This is what happens when you kill it with exit. Pressing Control-C sends SIG int. There's a lot of these different signals. So after you call exit, the OS delivers a SIG child signal to the parent process. The child is now a zombie process. It moves to the exited state. And what happens is it doesn't necessarily stop immediately. The parent process reaps it eventually, cleaning it up, calling the wait system call. This is a problem with processes that use network connections. If you don't kill them correctly, they can tie up a network socket for minutes. And this happens a lot in my other classes where we're developing hacking tools and port scanners and such. If you improperly exit from a network connection, you tie up a port for a while. All right, so here's the parent ID, which then calls a child, and the child hits an exit. Then it becomes a zombie, and sends a SIG child back to the parent saying your child has died, and it waits for the operating system to reap it. This, by the way, is quite similar to how stored data is removed from an SSD. When SSDs, when you delete a file on an SSD, that area is marked unused, and a garbage collection process will come by later, often 10 or 15 seconds later, to erase the data that's left over there. So if a child is still executing when the parent process calls wait, then it blocks, the parent blocks until the child exits, the parent enters the block state, and you can see it if you run a program in the foreground of a shell. The shell program is, so you start with sleep of 10, it's going to spend 10 seconds here waiting, and you won't get the prompt until it's done. All right. If you can also background things by putting an ampersand at. If I sleep 10 ampersand, it will start a process, run sleep, and put it in the background, and then give me a prompt again right away. So that's the game here. All right. So here's an example where you have all these. It's going to fork. It's going to print A for every program. Then it's going to fork and print B if it's a child. And that's going to fork again and send you down here. So you'll see parent A comes and forks, child comes and forks, it then executes something, then they all return. All right. So virtual memory is the abstraction. Each process has its own memory space, and in Windows, every program thinks it's running at memory location 400,000. But of course, they are running at different physical locations in RAM. It's a virtual address. The processes cannot access each other's memory space. They're each running in a separate container. All right. So two processes, you can run the same executable file twice. And if you do, they're going to have identical code, but as they run, they'll develop different data in the heap and the stack. And they're each, so if you have a variable called X here on the stack, and the other instance has its variable called X, those do not point to the same memory address, and they can hold different values, of course. Like you could open two notepad files and type different text into the two of them. All the data stored in the stack and the heap would be separate in the two instances. So like I said, virtual addresses are what you have. It program thinks it's running at a certain location, and typically 400,000 is where the program starts. Physical addresses are out here. the virtual addresses are here. So here's two programs of the same executable running, and they're both going to think they're running at the same location in memory, but in fact they're relocated by the operating system to different physical locations. So they think they have their own private copy of variable X stored at the same virtual address, which might be 1, 2, 3, 4, but they're actually stored in different real physical memory locations, and they're independent. So the memory managed unit is the part of the hardware that does this translation, keeps track of where things really are, so when the programs try to go to a certain virtual address, it will add some offset to them to find out where they are in memory. And the virtual address space is broken up into pages of 4 kilobytes, and so is all the physical memory. And we talked about this before. If you begin to run out of memory, you start swapping pages to the disk. So, all right, you have a page number and a byte offset, and physical addresses are also separated with a frame number and a byte offset. So you got the higher order bits determine what page you're on, and the lower order offsets determine what particular byte you're referencing within that page. So you have page tables for virtual to physical page mapping. It keeps track of where they are, and so it's possible that the pages are actually separated all over the place and scattered in memory. All right. And may contain other information, and there's a page table base register to keep track of where all the running process is. So processes tend to access pages of the memory space with temporal and spatial locality. If you've recently accessed some memory, you're likely to access memory near it. And if you access memory to a certain location, you're likely to access other memory near it. So that's an issue. So the operating system brings them into RAM when a process accesses those pages. And we talked about this before. When you're having to recover data from the disk, the operating system tries to be smart about it to bring it in because it's trying to avoid page faults. Now, I talked about context switches, where you have to store the state of one process to run another process. And that costs a certain amount of time and memory, but it's pretty fast because that all happens in RAM. But a page fault occurs when you have to load something from disk or SSD, which is much slower than RAM, and each page fault really costs you a lot of time, because then you have to swap some data back onto the storage device and read from the storage device. So you want to avoid these as possible. And so one thing an operating system does is use the least recently used policy, where when it has to empty a page worth of memory and make room for new data from storage, it will try to use the one that hasn't been used recently, hoping that you won't use it again recently, and therefore it won't have to swap it again. So to make it faster, you want to make this quick. If you use direct physical RAM addressing, each time every load and store requires 2 RAM accesses. You have to read the page table to get the frame number and write the bytes. All right. If you had direct physical RAM addressing, then you'd be faster. This is another way to go. If you ran without a page table, without any paging operation, where everything just has to be in RAM, then you wouldn't have these steps happen, but then you would not be able to run any programs exceeding your actual physical RAM. Anyway, the translation look-aside buffer is a hardware cache that stores these mappings. So your program tries to reach things, it looks up the page number and the page offset to track it down. So the processes are each running in their own separate memory space, and they can't see each other's RAM, so they need some way to talk to each other. One process may wish to say something to another. You might, for example, have a Word document open, and you click on a link, and now it's going to open that in a browser. So a signal from one process has to somehow get to another. So you can send a signal. This is one way to do it. You can have message passing, and you can have shared memory. 3 ways to do it. And so signals are like hardware interrupts. A trap is a synchronous software interrupt. Signals are asynchronous. A process may be interrupted by receipt of a signal at any point. All right, they're triggered by software instead of hardware devices. So here's some signals we talked about: segmentation fault, interrupt process, child process is exited, terminating a process, and so on. And when you shut down your machine, it just sends a signal. It doesn't pull the power immediately. That would be very destructive to the operating system. You avoid doing that. You send a signal saying, please begin an orderly shutdown. So when you receive a signal, the process can terminate, ignore, block, or unblock. These are the various things that can happen. You can change the default action of these signals, though. If you want to, you can reinterpret these signals to have a different meaning in your process. in their default. And you do that by writing signal handlers. So here's a signal has just come in. Here's a SIG alarm handler, which normally in old-fashioned computers it would make an audible beep. Then here's SIGCONT, SIGINT, so you can write your own handlers for these things if you want to. Register signal handles and repeatedly block. So you can have various options to write custom handlers for them. All right, and then there's messages. You can open a pipe, and then, so if you have a pipe here, like you're going to cat the contents of this file and feed it into something called factorial, then you have a pipe that takes the data from one process and feeds it into another process. It does it by writing it into a temporary file and then reading that file at the next end. That's called a pipe. And you can have a socket. This is a network connection. It can be done with networking or it can be done just in the operating system, where you open a socket to send and receive messages, and that's a channel to send and receive a stream of data between two processes. And you can do it with shared memory. You can specify that these 2 pages of memory actually map to the same physical memory, so when this process writes to this variable f, it will affect that variable f up here. This can be set up. So those are ways for one process to communicate with another. And let's take a look at another Kahoot. 13b. All right. And on Android, those signals are called intents. We studied quite a bit in mobile device hacking class. All right, when a process tries to access a page that is not in RAM, what happens? It's a page fault. They're pretty wasteful of time, and you try to minimize them. All right. How does the process communicate between 2 different computers? Well, I'm going to go back and look at the slides because I didn't expect that. Let me take a look and see. I don't understand how different computers can share memory. Let's see here, if I understand this. Inter-process communication. You can send to another process, that's right, but how can you possibly have shared memory send to another computer? I thought the only way you could do that would be with a network socket. And message passing. I don't think that can go to another computer either. So I wrote this question of processes on different computers to communicate. I can't remember what I was thinking when I wrote this. I might go look at my video from last semester and see if I can understand it. I am very confused by that one. If any of you understand it, let me know. Otherwise, I'm going to have to look it up. Maybe I'll tell you next time what I conclude. I no longer understand that question. The only way I think you can communicate between different computers is with a TCP/IP network connection. Anyway, all right, let's carry on. How about a one-way communication channel? Okay, this one I like. There's a right answer to this one. That's a pipe. The first program sends data to the second program, nothing comes back. A socket is two-way. There's a read and write channel. All right, that one makes sense. Chapter 13B, middle question. Seems wrong. Gotta look into that. All right. So we stop this recording.